Organizations that have successfully pivoted to the cloud have often found that their operations have also transformed in terms of tools, practices, and even organizational culture. Hi, my name is Frank Ang. I'm a solutions architect covering ASEAN and emerging markets. My previous role at AWS was as a software development engineer, and I'll be sharing a few practices behind the operational excellence culture at Amazon. Practices that are also increasingly used across many other AWS customer organizations. Now, cloud ops is actually a pretty broad discipline. In this 30-minute talk, I will dive specifically into the monitoring and observability aspects of cloud ops. Let's look at how metrics are essential for cloud ops and how metrics drives iterative operational improvements at AWS and for many of our customers. I hope you'll be able to take away a few of these ideas and adapt them into your organization. And speaking of organizations, since its early days, Amazon has used as a fundamental organizational approach the notion of small, autonomous teams. These are particularly useful for companies moving towards API-driven services and services-oriented architecture. By the way, in the quote here from Jeff, "It's too large" refers to the size of a team, not the size of the pizzas, just to clear that up. And these teams are structured around services. Hence, they're known as service teams, with separate delivery pipelines enabling teams to update and operate their services relatively independently. Standard API interfaces are extremely useful to balance autonomy with reusability across the services. Service teams consist of builders. A large proportion are developers, but teams can also have systems engineers, managers, and a variety of specialty roles. Service teams own everything about their assigned services, from design to code to tests to data to operational excellence. That sense of ownership extends to having every builder on the team being assigned to on-call operations duties on a rotating schedule. A central idea around the operational ownership was expressed by Amazon CTO, Werner Vogels, when he said, quote, "You build it, you run it." And running the service does present an operational overhead on teams. Most developers would much rather spend time shipping features instead of working on-call pager duty. Which is why Amazon service teams put so much emphasis on automation. This offloads the repetitive, routine parts of DevOps and saves valuable time so service teams can dedicate more time to work on the more interesting, higher-order tasks of solution analysis, design, and build. Automation uses metrics for continuous feedback across all stages. And it's useful to distinguish between health metrics and diagnostic metrics. Health metrics are super important because they indicate the level to which customers are being served properly. Health metrics indicate when the service becomes unhealthy, though we do need diagnostic metrics to pinpoint why the service became unhealthy. It's a good idea to set alarms on health metrics. Select just a few of the most important indicators as health metrics. For example, service availability, service performance. Diagnostic metrics, on the other hand, measures the behavior of the supporting resources. The next level down. For example, networking, compute, storage, database, supporting microservices, and so on. Diagnostic metrics are typically more numerous and varied. They are really useful for deep dive investigations. Now, to illustrate, let's investigate a few metric graphs. Here is a chart showing the count of HTTP 500 response codes, also known as faults. For example, 500 internal server error, 502 bad gateway, 504 gateway timeout. These faults should be fixed at the server side. And because these have a negative impact to the customer, these are health metrics. What we see is a perfectly healthy service with 0 500 responses, within the time frame at least. 0 faults is a good thing. Next, we see non-zero counts of HTTP 400 response codes. 400s also affect the customer experience and are also health metrics. 400s indicate client-side errors. What question should we be asking ourselves about the visible jump in the number of 400 responses? Was there a bug in a new update to the mobile client app just prior to the jump? Which type of error codes are these exactly? 400s, 401 unauthorized, 403 forbidden? Perhaps it would be worthwhile for a log dive to investigate. A transient bump in database transaction rollbacks. What happened here? Was there an aborted deployment that rolled back after an application update made suboptimal database calls? This is a type of diagnostic metric. It indicates a problem affecting a supporting service and a supporting resource to the overall service. Diagnostic metrics are very helpful for troubleshooting and can indicate subcomponents that need to be optimized, but are not themselves necessarily reliable indicators about the overall customer experience. Service latency. This is response time in milliseconds. Health or diagnostic? Clearly, it's a direct gauge of the customer experience and is a key health metric. However, be careful. The average is often a misleading statistic. The mean statistic is highly affected by outliers, so it's much better to use percentiles to measure latency. The 50th percentile, P50, or the median, is more useful. It shows the middle data points of the distribution. Even more useful is the 99th percentile, or P99. It's very useful for determining latency SLAs. This graph indicates that 99% of all requests meet that latency or better. P99 latency is a health metric. Weekly volume. This is the count of requests into the service. Here we see the amplitude pattern of normal, weekly, and daily volume. This can help us with auto-scaling tuning decisions. Now, let's overlay latency over volume. It appears that increasing volume is correlated with poorer latency. Even jitter gets worse at higher volume. Why? Where is the limiting factor? Is auto-scaling configured correctly? Is there a bottleneck in the application code? Is there a limit in a downstream dependency? Is there a constrained backend database? And is this an early warning sign of a tipping point about to happen? Another example, P99 latency. Consistent low response time. That's excellent. But what's wrong with this picture? The alarm threshold is too high. How did it get so far above actual? Well, perhaps there was a very effective performance improvement recently. That's great. But the corresponding alarm adjustment was missed. What if a real problem occurred down the line? Would the alarm miss it because the threshold is too high? There, that's better. Now the team is more confident to catch sustained latency anomalies. It's a good idea to review alarm thresholds periodically so that we can reduce mean time to detection. So now that we've selected our health and diagnostic metrics, it's time to put them together up on the screen. When designing ops dashboards, health metrics should be at the very top, obviously. Diagnostic metrics are supporting, so it's okay to scroll further down the page, or even have a separate diagnostics dashboard. Service dashboards consolidate the most relevant metrics that matters for a team on a single pane of glass, making it a lot easier to visually correlate information and find patterns, giving operational visibility when it really matters. And at AWS, we use dashboards a lot, particularly at every weekly engineering ops meeting. So the rough agenda of this meeting: we always start with successes. Success stories from new launches to even operational wins, such as technical wins that ultimately benefit customers, reduced error rates, reduced latencies, efficiency gains, performance optimizations, major upgrades, or improvements that reduces operational work for the service teams. Next, we also go over group-wide announcements or AWS-wide projects. Though the majority of the ops meeting time is spent reviewing service metrics and reviewing any operational events. These are really important to find lessons learned and improve the services further. Each operational event is captured in a correction of error, or COE. This is Amazon's process of root cause analysis and operational improvement. After an operational incident is fully resolved, the team will write a COE. The center of this document is a questioning approach called the 5 whys. It's a cause and effect analysis to find the set of root causes behind a problem. It's not for finding whom to blame for the problem, no blame, and no individuals named, but rather it aims to objectively find the lessons learned and to identify actionable improvements to systems and mechanisms. Let's illustrate an event where the availability of a service has been affected. Service availability metrics show a dip. There's customer impact during the period and subsequent recovery back to 100%. So clearly, the aim should be to reduce the impact period to as short a duration as possible. Let's dive deeper into the event itself and the 3 stages within a typical event. The first stage is the time to detection. The COE asks standard questions such as, how was the event detected? How could time to detection be improved? Alarms and alerts are clearly essential here for early warning. And remember, set alarms on the health metrics. Another helpful technique is continual synthetic testing in production, sometimes called canary testing. Just like a canary in a coal mine provides early warning. The second stage is determining how to mitigate the impact. The team uses the available data to understand the issue and decide on the best course of action to restore the service quickly. And the third stage is to actually execute the mitigation activity. Oftentimes, there's automation in place and all stages are performed automatically. All good. And a COE is not required in such cases with minimal customer impact. However, when a novel event does happen, the team needs to figure out the new situation and take corrective actions. Again, dashboards are super useful. The team might check for events internal to the service, for example, recent deployments, and figure out how external service dependencies are doing. Where metrics are insufficient to determine a mitigation, it may be useful to perform a log dive for further observability. And that's where centralized logging and search become really useful. The team, or operations on call, executes the mitigation activity to recover the service. And after event, we analyze the timeline and collect the relevant facts into the COE, and we move on to root cause analysis. The 5 whys approach was originally developed at Toyota as their problem-solving technique to improve the manufacturing process. Amazon has also adopted it for its root cause analysis. 5 whys approach is a very simple and effective iterative questioning technique to explore cause and effect relationships that's underneath a particular problem. It acknowledges that the initial problem statement is often only a symptom of deeper issues. Take this example. The car won't start. By iterating through asking whys, diving deeper into cause and effect, we arrive at a set of root causes. The COE closes with the lessons learned and a list of corrective actions. These are action items, such as better test coverage, improvements to scalability, improvements to monitoring, security, or even added automation to reduce the surface area where human error can creep in. These actions are assigned owners, assigned target dates, and are tracked to completion. The correction of error process is a central part of how Amazon maintains a high bar of operational excellence. And many AWS customers have also developed their own operational cultures with similar levels of rigor. And AWS customers have a choice of tools to implement cloud monitoring. I will apply several of these best practices through a few AWS native capabilities, such as CloudWatch and X-Ray, in a simple, fast demonstration. Here is a React.js front-end web client. Super simple. It calls several RESTful backend APIs that returns a random quotation. User requests land on an API gateway, routes to a load balancer into the compute layer, and data access to backend databases. All components in the system are instrumented for CloudWatch, emitting metrics and sending logs to CloudWatch. Alarms are set up on health metrics to reduce time to detection. Abnormal conditions trigger an alert to the ops on-call person. An investigation determines whether any mitigation activity should be executed. A canary keeps an eye on the service, continually testing it for quality. Now, let's take a look at applying what we learned about Ops dashboard design. Click on Dashboards at the top of the CloudWatch console navigation pane and select our Service Health dashboard. Health metrics help to measure the quality of the service as experienced by the customer. Let's resize things. Be mindful of the time range. Different time ranges often show complementary perspectives. Remember, when in doubt, zoom out. You might find patterns, anomalies, and trends to take note of. This team has decided to use 4 main health metrics: volume, latency, errors, and faults. The overall view at the top of the dashboard page, arranged left to right. Firstly, requests volume, the count of requests hitting each API every 5 minutes. A 1-minute resolution is also possible in CloudWatch. Latency, P90, errors, 0 errors is good, and faults, also clean, at least within the selected 3-hour timescale. Individual services. Individual APIs are further down the dashboard. Could be registration, search API, checkout API. We're just calling them red, green, and blue. Super simple. The distribution of latency becomes clearer by overlaying different statistics, like P99 and P50. Notice the alarm thresholds are also overlaid. Canary tests. 100% success and reasonable latency across the multiple synthetic test scripts. Let's switch to the diagnostic metrics. This example has moved the detailed diagnostics into its own dashboard page. We see detailed resource metrics for the subcomponents, such as network load balancer layer, compute layer, auto-scaling group instances, the usual instance metrics. Wait, we spot the need to optimize memory usage. Better add that to the work backlog. Various databases and their metrics might want to improve the vertical y-axis scale on CPU utilization, which makes it look more complicated. It's actually quite stable. Another memory usage trend, and it's also possible to embed CloudWatch logs insights on the dashboard too. Diagnostic metrics are useful for deeper dive observability about subcomponent behavior. CloudWatch dashboards can be shared for control room type visibility. Here, we configure a Cognito user pool to authorize dashboard viewers, and AWS single sign-on is also supported. This enables dashboards to be shared across teams, display dashboards on big screens in team areas, or embed dashboards in wikis and other web pages without requiring access to the AWS console. Now, to regularly monitor your endpoints and APIs, even outside normal customer traffic hours, you could use Amazon CloudWatch synthetics to create canaries. These are scripts written in Node.js or Python to perform the same actions as a real customer. The effect is to continually verify the customer experience. This helps discover issues, potentially before a real customer does. You see, the runtime type and scheduled frequency are configurable. Canaries can run inside a VPC as well. And at runtime, Canary runs periodically, performing tests, and we see the results of the various Canary tests, all successful here within the past 3 hours at least. Now, selecting one of the canaries, we zoom out to 1 week, and we discover test failures. Why? Well, here's the actual API JSON response. Let's say one of the API clients had a bug that started sending invalid requests. The service responds with 400 error response codes. This trips off the alarms. So the ops on-call team member receives the alert and goes in to investigate. To reduce alarm noise and focus on critical operational issues, multiple alarms can be combined together into alarm hierarchies, called CloudWatch composite alarms. These only trigger once the multiple alarms that match fire at the same time. This reduces alarm fatigue and helps service ops personnel to stay focused on finding the root cause of operational issues. Here we see the matching conditions. For example, this is one of the alarms that triggered the composite alarm. We click into the detailed metrics. Okay, let's investigate to find out more about these errors. That's where AWS X-Ray is really useful. So in the service map, let's go have a look at that. Here we see the graph of calls across services, and some are native AWS services like API gateways, canaries, and others are applications that have been instrumented with the AWS X-Ray SDK. Centering on the service graph and centering it on the API gateway, we find that 14% of errors has happened in the last 6 hours. 37% of errors have happened in the last 1 hour. And in the last 15 minutes, 47% of responses resulted in errors. The canaries kind of look okay, so most likely the errors are probably actually affecting an actual user. The API gateway and 2 of the microservices show orange error indicators. Let's try to find the affected API calls. So, service lens traces helps us to explore and filter down to find the service calls that interest us. Multiple ways here to filter the request traces. These are the individual traces. The multiple filters are on the left. 37% of traces have errored in the past hour. Let's filter down to include only the errors. Let's also look at the other possible filters and HTTP method. We know that the API uses a particular HTTP verb, a get method, so let's filter to that. We also want to filter and just look at the 400 range of error responses. And after filtering, we can see and identify the affected client IP addresses. Let's pick one of the error traces. Okay, so see all of these are the remaining filtered traces, and at the segment's timeline, we reveal the duration of time of each segment within a multi-step trace. The backend's a Golang microservice, and it's unable to parse the request. So that part quickly returns 400 errors in sub-millisecond. Let's do a log dive into the CloudWatch logs collected. Jumping into CloudWatch Logs Insights helps us quickly and interactively search and analyze log data. Let's select the CloudWatch log group for the application and filter to find the recent logs containing matching IP patterns using a simple regular expression. And we find the matching error messages in the application logs. The service team reaches out to the external application team. The bug fix is deployed for affected customers. Alarms are cleared. And we have a root cause to share with the group during the next weekly operations meeting. We've taken a look at AWS native services, such as CloudWatch and X-Ray for monitoring and observability. Though the concepts would still apply even for other tools such as Elasticsearch, Kibana, Prometheus, Grafana, or solutions from AWS ISV partners, such as Splunk, New Relic, Datadog, Dynatrace, AppDynamics, and others. And I did mention earlier that CloudOps actually encompasses a pretty wide range of concerns, beyond monitoring and observability, including change and configuration management, release management, security ops, reliability ops, to financial ops. And AWS, along with our ISV software partners and SaaS partners, have solutions available for these areas. To close, operational excellence can be ingrained into culture. It helps to have an organization that is truth-obsessed around metrics and data, that trusts builder teams with ownership, using data to drive operational decisions. And metrics data can be classified into health metrics and diagnostic metrics. May I suggest to consider adding an operational excellence review to your team's work backlog. Review your approaches to metrics dashboards, to central logging, alarms, canaries, automation, and even consider which Amazon practices you can take back and adapt into your organization. Also consider the tools that are right for your requirements. Oh, and just one more thing. To gain more confidence and hands-on experience with AWS, access the digital training built by AWS experts. Attend our instructor-led classes by qualified AWS instructors, and learn how to design, deploy, and operate highly available, cost-effective, and secure applications on AWS. Validate your technical expertise with AWS and use practice exams to help you prepare for AWS certification. Thank you again for attending. And we really appreciate your feedback, so please do take the time to fill out our survey and let us know your thoughts, so that we can improve the AWS Summit experience for you in the future.